So I just want to go over a little bit about programming and the project. So the first thing to notice is that this is going to look very similar to the project template, or this basically is a top project template. As you can see, I've just made a copy. So that's what you're going to have to do as well when you do this. If you can either download the template that I put in Canvas, or if you go to the link, you're not going to be able to modify it. You're going to have to open a copy, which you do by coming over here, File, uh, and then save a copy, and Drive will open a copy. So if I do this, I think it'll say like copy of Math Project 301, another copy. Okay, so I'm going to get rid of that and come back to this. Anyways, so that's how you do it. Now, what is Google Colab? So Google Colab, if you're not familiar with it, it's like Jupyter. If you're not familiar with either one of those, let me kind of tell you what that is. So we want to do programming, right? So programming, you're writing code that some other software, in this case Python, knows how to take that and interpret it into eventually into machine code, zeros and ones and that sort of thing. That the computer then knows how to do. Well, what the computer instructions that the computer then knows how to execute. Now, there's a whole lot of intermediate steps, and none of that matters for what we're doing. But the point is, you have some sort of structured language in which you're writing it. In this case, it's going to be Python, and then there's an interpreter that knows how to take that and get the computer to do it. So there are several ways that we can do this. We could write it just kind of in a text file and tell Python, hey, look at this, and execute it. But a good way that I found, a very good way, just for a number of reasons, but especially for something like this, is going to be either Jupyter or Google Colab. Again, very similar things. And this is sort of like the power of a high-level programming language like Python, combined with the flexibility and the kind of ease of use and kind of immediate answer of a calculator. So it's just like a very big calculator in a sense, a calculator that can do far more, a calculator that in some sense can do far more things than like a TI-84. Okay, now, if you want to get technical, there's probably not anything that this can do that a TI-84 cannot technically do. Just this is way, way easier. Okay, and what I mean by that is like some theoretical computer science thing about Turing completeness that I don't really know about. Anyways, so what we're looking at, this right here, there are several lines throughout this document that says don't change anything below this. So every in Jupyter Notebook, there's going to be all of these different cells. Each one of these cells can do a computation. So let me even start off with something even easier to use. So, or not easier to use, but just even more basic. Okay, so it opens up with this AI thing. To open that, you click this, and it'll open up Gemini. So this, for example, I'm kind of testing out how you might use Gemini, and I just basically copied one of the cells below, and it gave a somewhat good response. Okay, so let me just give you an example. So let's say I want to do 7 times 5. Okay, I'm going to click run. This here runs the cell, and it's going to display 35 below. Whoops. Okay, so obviously it's a slow calculator. I think it might be like loading the thing when you start off here. Okay, so I come over here. If I want a new cell, I can come up here and do code. Let's try that again. 7 times 7. Okay, so I think that first run was just kind of loading the software. So this is how we can do things. Now, one thing that is good for programming is that we can have variables. So I can say x is equal to 5 and y is equal to 7, and then I can do x times y, and when I run this, it's just going to give us 35. Okay, very good. So if we come back over here to the project, this first cell, we have some code that we're executing. This says import numpy as np and import matplotlib.pyplot as plt. So what is that doing? Well, there's a lot of stuff that comes standard with Python, but these are additional packages that have additional functionality. that we might want to use, and that in this project we definitely will use. Okay, so you're not going to modify that at all. So if you look at this cell right here, notice what's happening. There's a whole bunch of stuff going on. So this right here is called a function. Euler method is the name of the function. It takes in 1, 2, 3, 4, 5 different parameters, and it's going to return something. So it takes in 1, 2, 3, 4, 5 different parameters, and it's going to return something. Okay, so that's what a function does. It takes in values and it returns values. Okay, so computer programming, there's maybe a more general notion of function than you have seen like in mathematics and that sort of thing. This is going to take in these 5 parameters. Now, f is itself another function. It is the right-hand side of the equation, y prime equals f of xy. X naught is the initial value, so this is the initial value, y of x naught is equal to y naught. That's what these initial values are. H is the step size. We talked about that in the, or I mentioned that. You can even see it up here on the whiteboard behind me from when I made the video on the Euler method. And then x end is going to be the end, the last end point. Okay, now the project you have will not have any of these things right here. I'm giving you a head start. I'm giving you 3 lines of code. I think there's like 5 more lines of code that you need to write to get this method working. Okay. So in steps is the number of steps. Now, there's a number of ways to do this. I don't know if this is the best way to do it. And in fact, you can change the function definition here. Essentially, what we need to figure out is we're going to go from x naught to x end, and we're going to be incrementing by steps of h. Okay, now if you think about what's going to happen here, if h, there's no guarantee that for a given x naught and x end that an integer multiple of h steps are going to get us up to x end. Now, in this case, in the case of the problem, it will, because x naught is an integer and x end is an integer, and the step sizes are going to be like 0.1, and so there's always going to be an integer number of steps to go from x naught to x end. But it doesn't have to be that case. If x naught was like, well, whatever, I'm not going to go over that. But for this problem, for what we're doing, there's always going to be an integer number of steps, an integer number of increments of size h to go from x naught to x end. Okay, so how many steps are there? Well, it's basically going to be x end divided by x naught divided by h. Okay, but again, what happens if x naught, what happens if x end minus x naught is not a multiple of h? Well, there's 2 things that we could do. We could either go one step, we could go to all of the h steps up to the last one before end. In other words, let's say h is 0.25, and we could either go from, maybe we're going from x naught equals 0, and x end is equal to 0.7. So you go 0, 0.25, 0.5, and then that would be the last step. Or we could do 0, 0.25, 0.5, 0.75, and go past. So we have to decide whether we want to end the step before x end or the step after x end. And this is, again, only for the case where there's not an integer number of steps of increment h to go from x naught to h. So again, an example would be if x0 is equal to 0, x end is equal to 0.7, and h is equal to 0.25. There's not an integer number of steps to go from 0 to 0.7 in increments of 0.25. Okay, so you can either go to 0.2, you can either to go to 0.7. So you can either go to 0.5 or you go to 0.75, but you can't go to 0.7. This right here, np.ceiling, it takes the ceiling. This is the ceiling function of this thing right here. So this is rounding up. So what this is saying is we're going to go a little bit, instead of going, ideally we would end at x end, but instead of ending before x end, we're going to end after x end. And now this is by default going to be not an integer, and so this int right here just says let's convert it to an integer. So instead of this being 3.0, it's just going to be 3, and that's going to be important. That's going to be important for stuff down here. We want the number of steps to be an integer. Okay, now xs is equal to np.zeros in steps plus 1. Okay, so what's going on there? So I'm going to come over here and I'm going to import numpy. I'm just going to write import numpy. I'm not going to write import numpy as np, and you'll see why in just a minute. So let me run that. Shift enter will also run the code. Shift enter will run the code. That's what I just did. Shift enter will run the code and give you a new cell. Okay, so what is numpy? So I'm going to basically copy some code like this. Let's say that now we have a program that will compute in steps for us, but let's say in steps is equal to 5. I'm going to say that xs is equal to in numpy dot, see, Gemini is already giving me an idea. Now it doesn't know what I'm doing, so none of this makes sense, but it's interesting what it's giving me. Anyways, so we're going to do zeros. xs is equal to np.zeros in steps. Okay, so now we're going to run this. Okay, so what is xs? If I just type xs and then run this code, it's going to give me what xs is. So in steps is equal to 5. So like, according, in Python's world, that in steps can be replaced by 5. And notice what it does. It gives me a list or an array of 5 numbers that are all zeros. That's what numpy.zeros does. It gives me an array of all zeros, and the number of elements in that array is going to be whatever that number is there. So if I did in steps plus 2, it's going to give me 6 because, or sorry, 7, because in steps is 5, we add 2. Okay, and that's what this line of code is doing here. xs is equal to np.zeros. Now the reason that I have, so this will come up in the differential equation. Sorry, this will come up. This is something that I wanted to mention as well, but I will get to that in just a minute. Okay. So here I have numpy.zeros. Here I have np.zeros. Okay, so let me take this away. Hold on. Okay, this will be a little bit easier for me to deal with now, so I don't have as many tabs to deal with. Okay, so here I write numpy, and here I'm writing np. Okay, so why is that? Well, it's kind of a pain to have to write numpy each time. So up here we have this statement, import numpy as npy. Here I just have import numpy. So when I say import numpy as npy, it just means that instead of writing numpy, I can write np. That's all it's saying. Okay, so we've got xs is equal to np.0 in steps plus 1. We have ys is equal to np.zeros in steps plus 1. Now, this is the code. One of the things that I want to illustrate here is this is the code that Gemini gave me. Now, there's nothing wrong with this code at all, and it works completely fine. In fact, down below, I've written this exact function, or I've used the exact function that Gemini gave me. This is not the way that I would do it, but I'm just trying to illustrate that it will work. Okay, so whatever you put here, you're gonna have to figure out what code to put here based on what Euler's method says it should be. Okay, but the point is we're going to iterate over these two vectors, xs and ys. Okay, so what does iteration mean? Okay, so what I'm going to do is I'm going to do the following. I'm going to say for k less than in steps, I'm going to do something. Okay, now this is what we want to do, but this is not going to make, sort of idiomatically, this is what we want to do. We want to say for k less than in steps, we're going to print k. But there's issues here, it doesn't know what k is. So when I run this, it's going to give me a few errors. Okay, so it doesn't know what's happening here. So the way to handle this, there's, again, several different ways to do this, is we can say k is equal to 0. And then we can say while k is less than in steps, we can do something. In this case, I'm just going to print k. Okay, so there's an issue here because I'm saying, well, k is less than in steps, print k, but I'm not incrementing k. So I'm going to say k is equal to k plus 1. Okay, it's going to print sorry, let me put it here. K equals K plus 1. Okay, so 0, 1, 2, 3, 4. Just printing it out. Now what we're going to do is we're going to say XS of K. We're going to say XS of K. We're starting with 0, so XS of K is going to be 0 plus K times, times H, where H is the step size. So let's say H is equal to 0.1. So now if we run this, I'm not increasing K again. So K is equal to K plus 1. We're going to get this, and if I look at XS, I'm going to get this vector. Oh, let me change this back. Okay. Okay, and so we get 0, 0.1, 0.2, 0.3, 0.4. Okay, so if we're going from x equals 0 to x equals 0.4, these would be the x values. Okay, and now what we can do is we can say ys of k. Ys of k, now I'm not going to type this out for you because I want you guys to think about it. This, I'm going to type out something that's not going to work. This is going to be equal to ys of k minus 1. This is not going to work. Plus f of xs of k minus 1, ys of k minus 1, and then times the step size. Now, this is not going to work out for a number of reasons. We haven't defined what ys is, but we can come up here and do that. We could say ys is equal to numpy.zeros in steps. It's telling me already. That's going to be okay here. But one of the real issues is that I think this is not going to give an error, but it really should be giving an error. Oh, I haven't defined what f of x is. Okay, so sorry, let me do that now. So define f of xy, and I'm just going to return x. So this would be like the differential equation. I'm going to return y. Sorry, this would be like the differential equation. Y prime is equal to y. So if I come here and run this, okay, now it's not giving me an error. Now this is even sort of worse than not giving an error, because we're starting when k is equal to 0. When k is equal to 0, we have ys of minus 1. Now for a list, the first index is the 0th index. That's the 0th index, the 1th index, the 2nd index, the 3rd index, the 4th index, and so on and so forth. So the -1 index does not always mean something. For like other programming languages, there would just be an error because a -1 index doesn't mean anything. However, for Python, the -1 index just means it refers to the last index. So everything works right here. Everything works in the sense that it doesn't give us an error. Now, like I said, this is almost okay, but the issue is that we don't want to start when, the issue is that we're starting when k is equal to 0, but we want to start when k is equal to 1. Now if we run this, again, we're going to have something that makes a little bit more sense. So if we look now at ys, I do not see what the issue is here. Well, this is great. Normally I get to be embarrassed when I'm writing code when I'm in front of class, so I guess I can't see your faces now, so maybe I'm less embarrassed. Okay, so here's the issue. So if I look at ys, the first entry here is going to be is going to be y of x naught. It's whatever the initial value is. So it's saying the initial value is 0. So I'm essentially implementing a numerical method to solve y prime is equal to y. So I know the general solution is c times e to the x. And I'm saying the initial condition is saying y of 0 is equal to 0. So the only solution is a 0 solution. So it did exactly what I wanted it to do. So now that's what y of s is. But I want to say that y of s of 0 is going to be equal to whatever my value is. So in this case, I'll say y of x naught is equal to 1. So I'm going to run this. And I want to type in ys. It's going to give me that. Okay, so now when I run this, it should give me something a little bit better. Okay, now ys, this should be the approximation to the solution to y prime is equal to y, with y of 0 is equal to 1. In other words, this should be the approximation to y of x is equal to e to the x. Now, what do I mean by that? Well, if I type in xs, what this means is that 1 is roughly equal to y of 0, 1.1 is roughly equal to y of 0.1, 1.21 is roughly equal to y of 0.2, 1.331 is roughly equal to y of 0.3, and this is roughly equal to y of 0.4. Okay, now I want to change things slightly. Now the algorithm that I have set up here is, I've set up things slightly differently than I have set up in this right here. You can use this, or you can use something closer to this. I don't really care. The only thing that I do care is you can't change any of these parameters. All right, so what are we doing over here? I'm going to make the number of steps, because now I'm only going up to 0.4. I'm going to make the number of steps equal to 10, and I'm going to keep, where did I define each? I've kind of defined, I'm doing a lot of bad programming practices here. So we're going to look at this. Okay, so this is ys, and the initial value is going to be equal to 1. And then I want to look at xs. So this gives me xs. Okay. Anyways, all right. So here I'm just going to set ys. I actually was not planning on doing it like this. That's why things are a little disorganized. Okay, so I'm going to get rid of this cell because it's not doing anything anymore. So I'm going to do this, and now I'm going to do this. And now if I look at ys, there's going to be 10 elements in it instead of just 1. And if I look at x, there's going to be that as well. So in other words, what it's saying is that this is roughly equal to y of 0.9. And actually, I'm going to turn this up to 11 steps, because if I see this, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But actually, I want to go from 0 to 1. So I'm going to do this again, this again, this again, and this again. Okay, so in other words, this number right here is roughly equal to y of 1. In other words, that should be equal to e. And that's a pretty good approximation. Okay, so now I want to introduce how we can actually graph solutions. And that's what this import statement here does. This says import matplotlib that pyplot is plt. Now this is plotting. The very basics of plotting is easy. So we're going to do plt dot plot xs ys. This is all this is going to do is it is going to we have the x vector and the y vector. It's going to look at all of these ordered pairs, and it's going to draw a dot at 0, 1, at 0.1, 1.1, at 0.2, 1.21. It's going to draw a dot there, in a sense, and it's going to connect each one of those points with a line segment. So this should just give me something very simple. I did not run this code yet, so before I put it there, but I didn't run the code, so it didn't actually get loaded in. So now I'm going to come down here and try again. Okay, so that's exactly what we got. Now this looks like an exponential curve. But let's say we want to see whether or not it's an exponential curve. So we're going to do plt.plot. We want to see how close it is to the exponential curve. We're going to do xs. And now I want to do, for each element in the list xs, I want to do e to that power. Now the way that we can do this is np.exp of xs. Now numpy.exp of xs. So what this is going to do, for every element of xs, So it's going to create a new vector, or a new array, and the corresponding elements of that array, and this array right here is a new array. It's just going to be that raised to the power of v, that raised to the power of v, e raised to that power, e raised to that power, e raised to that power, so on and so forth. So I'm going to run this now, and we see we get two different lines. Okay, now we don't know which color is which. Before, the blue went with this, but we don't know if it's changed. So how can we change that? So I'm going to do color equals blue, and this I think should work, and color equals red. These spaces aren't necessary, but I like to put them. And so if I've done everything correctly, the blue curve is going to be the approximation curve, and the red curve will be the exact curve. Okay, so this is the exact curve, this is the approximation curve. And we can see that you can analyze, you can look at this and analyze what's happening. Notice what's happening is that as as we get farther and farther away from the beginning point here, the solutions diverge, because as I mentioned, there's the errors are actually compounding and adding up. Okay, so if we so I'm going to increase the number of steps to 101, divide this, everything should work properly here. And now notice I'm going from 0 to 1, but I'm going in increments of 0.01 rather than 0.1. When I run this, I think my assumption is that these two curves are basically going to lie on top of each other for the whole time. And they do, almost, but again, you can see what's happening towards the end point. You can see how things are starting to add up. The errors are starting to add up, and we get this. And we start to get divergence. Okay, so that in this function right here, you're going to implement Euler's method. Now, like I said, you could just come over here and type something like this, but like copy and paste this cell, paste it over here and say, tell me what the answer is, and it's going to tell you the answer. Now, it gives it in a way that I wouldn't do it, which I think can sometimes be okay, but sometimes I think this is just a little bit too confusing. So if you know what you're doing, I would suggest not even thinking about this, or if you know what you're doing, or if you don't know what you're doing and you don't want to just use Gemini or something like that, and want to try to learn things a little bit more, Google things or whatever, just think through it. But Gemini will give you the answer if you just want to sort of see what the graphs look like. Okay, now down here what's happening, we've got f of xy. This is the right-hand side of the differential equation. So it's y prime is equal to y minus x squared plus 1. And we can solve this. The exact solution is this. With initial value y of 0 is equal to 0.5. This is the solution to the differential equation. Y prime is equal to that. With initial value y of 0 is equal to 0.5. Now don't touch this. I mean, you can touch this, okay? But when you turn it in, put it back to this, because that's what I'm going to put. Okay, so you need to make sure that it works for this, but you also need to make sure it's going to work for other things as well, because I'm also going to check it for other things as well. Okay, so just try a few different examples, and your solutions should roughly match the solutions. Your approximate solutions should roughly match the exact solutions, and it should sort of, as x goes on, it should match close to x naught, and as x naught goes on, we would expect that the difference is going to increase. The difference between the approximate solution and the actual solution will increase. Okay, so now what's happening here, this is just plotting like I did here, but it's plotting with a bunch of different options. And you can read through what these options are, but I just wouldn't touch it. And we're going to run it. Let's see, is it going to work? So I have a different function here. Okay, so, and again, we can see what's happening here. This is the approximate solution. This is the exact solution. With h only equal to 0.2, which is a pretty big step size, we see that the divergence happens here. If I change this to 0.1, when I say the divergence happens, it's just because it's late. I know that doesn't make sense. It's almost 10 o'clock. I'm normally done doing math by now. Okay, so when I say the divergence happens, I know that is like a really weird thing to say and doesn't technically mean anything, but the divergence happens when I say that. What I mean is that we're starting off close here and getting farther and farther apart this way. But if I change h to 0.1 and run it again, it's closer. If I change to 0.01, it's going to be even closer. Now you can't even see the difference between the two. Okay. And in fact, for something like this, the O's are what gives it the O's there. And since there's so many O's, it's kind of crowded. So I'm going to take this away and run it without the O's. And now we can see the orange is the Euler method, and the blue, excuse me, the orange is the Euler method, and the blue is the actual solution. And there's a question down below about whether the Euler method gives us an over approximation or an under approximation. And you can think about maybe why that might be. Okay, so just remember what is in the algorithm. There's this f function that we're doing. And if you're wondering, if you understand a little bit about what's going on and you're trying to figure out what's happening here, well, Euler method, I've defined it way down below. So it's not using this Euler method up here. It's using an Euler method that I have defined in cells way down below because I just want to illustrate it. Okay, and now you can look at this, I guess. That wasn't my plan, but all right. Wait, I'm not sure what's happening now. Oh no, this is just somehow the same cell twice. This is because I have no idea what is happening there or why it's like that. If that's in the project, I'll get rid of it. Okay. So now, this is the thing that I wasn't planning. In the cell below, it will print the, oh wait, is that what? Yeah, I don't know what's happening. The cell below will print the difference between the exact solution, the approximate solution for these step values. So I guess you can just use this. But again, this is what I showed you that Jim and I had done before. Okay. I think maybe not. Anyways, it gives you this, and now you have various questions to answer. You have two questions to answer. You're going to answer this in complete sentences. Both of these answer in complete sentences. Okay, and now essentially what you're going to do is you're going to run through several of these last cells, but with a different function here and a different solution. So that was the Wolfram alpha cell that I showed you before. It's just a solution to y prime is equal to 5y minus 6 to the power of e to the minus x. Clearly, this is something that we can solve using integrating factors. It's not very difficult. Now, what's going to happen with this? I'm not going to show you much below this because I want you to do it for yourself. What's going to happen with this equation is called a stiff differential equation. And essentially, the way that we can think about stiffness is that the coefficient on y is big. But the problem that we're going to have here is that if we solve this with the initial value y of 0 is equal to 1, that solution is going to go to 0. We know it goes to 0 just by solving the differential equation. We can solve this explicitly. On the other hand, what's going to happen? Well, on the other hand, I want you guys to see what's going to happen. We know analytically that the solution should go to 0. But I want you guys to see what happens numerically. Do we have an answer that numerically goes to 0? Or do we have an answer that does something different? So numerically, the answer should go to, it should decay to 0 very quickly because y of x is equal to minus x. So you should get a very quick decay to 0. But when you implement it numerically, I want you guys to see, does that happen? And can you ever make it happen? Can you always make it decay to 0 by making h sufficiently small, or is there always going to be a problem? And then I ask you to analyze that a little bit. So for example, one way to analyze this would be to solve the initial value problem. Y prime is equal to this. For y of 0 is equal to y naught. For y naught is just like an arbitrary value. And then see what the differences are in that solution and the solutions that you get. See what the difference for, see what the difference in the solution is going to be for y naught is equal to 1 and for y naught equal to any other value. And then if you analyze that, you'll be able to get a glimpse of what's going on. Another good thing, which I'm not suggesting that you would do, or that you have to do, is to think about what the direction field looks like. Anyways, okay, this is a very basic overview of this project one. If you've not had any programming before, again, I think it's going to be a little more challenging for you. That's just obviously going to be the case. But please come to office hours, talk to friends, go to the Math Learning Center. There's Python help in the Math Learning Center and stuff like that. But I think, learning these numerical methods is one of the most important things because many engineers are going to use these numerical methods. Anyways, and so understanding the pitfalls also is something that's important as well. Okay, so that's going to be it for this video.